So it gives me great pleasure to introduce Aaron Hertzmann. He's a principal scientist at Adobe Research and also an affiliate professor at UWash, University of Washington. For many years, Aaron was a professor at University of Toronto before joining Adobe, and he has worked with many of the top labs in the world, including Pixar, Microsoft Research, Merle, and Interval Research. Aaron received his BA in computer science, in art and art history. So that's a very unique combination, and we'll get to that in a bit. From Rice University, he then went on to receive his PhD in computer science from NYU. Aaron's work during his thesis as a PhD thesis and subsequently opened up this radically new idea of painterly rendering and NPR. So he's associated with starting this line of work. And I still remember my early days as a PhD student when everyone was trying to get like photorealistic rendering. I remember the SIGGRAPH cover where Aaron had this painterly rendering and opened up this new area. And much of today's workshop is around this theme of sketching and how do humans sketch. Aaron is a fellow of ACM and IEEE, and he's also the editor-in-chief in Foundation and Trends in Computer Graphics and Vision. His research works around creativity, how humans draw, and he brings in insights from both like artist workflows and of course, data-driven machine learning applications. So today he's going to tell us why line drawings really work. And this is going to be exciting. Aaron, over to you.
Great. Thank you so much for the kind introduction and for inviting me. So you should be seeing my slides and hearing me okay. Let me know if that's not the case. And the work I'll present today was published in a Perception Science journal in 2 papers last year and this year. And so the question here is really, why do line drawings work? How does human perception of line drawings work? And even though this is not directly about sketching and sketching interpretation, I do think that better perceptual models of line perception could lead to better perception algorithms for inference of line drawings and better sketch-based modeling tools, although I won't speak to that directly. So I want to begin with some things we know about visual perception. We believe that our perception is, in a sense, optimized for real-world scenes, that we are evolved to navigate and survive in the real world, and vision assists us in this goal. And so we can look at images like this or see these scenes in the real world that have unfamiliar objects and unknown lighting, and from a single glance, interpret what the shapes are and interpret what the lighting is, interpret the materials of the objects, all in a very immediate, very fast way. We don't need to have seen these things before, as long as there are things that could occur in the natural world. So then line drawings present a bit of a puzzle because they're not things that we see in the real world. We don't see these sort of black and white outlines moving around in our natural environment. We're not evolved to see these things moving around. And the idea that we would have seen these as part of our evolution is a little hard to believe. So why is it that we perceive shape and line drawing so easily? And not, for example, why don't we just see these as, say, black marks on a white page? If you like doodle or draw, a very abstract set of curves, you could just see those as black and white curves on a white page. And yet, if you make a drawing of an object, people will perceive that as a recognizable shape. And so the question is, why does this work, given that this is not part of our evolution? There's only been a few, this is something people have talked about in philosophy for a long time, and there's really only a few kind of theories people have formed. One is the idea that depiction styles are learned, that just like we learn written language, we learn the alphabet and so on, we also learn to understand art, and we learn to understand drawings. And so this seems plausible at first, but I kind of don't find it very persuasive, in part because we see drawings throughout all human history and in prehistory. And there seems like there's a lot of commonalities between the kinds of drawings people do in different cultures. But even more concretely, there have been a variety of studies where people have found members of tribes or other individuals who have never seen a drawing before, and you show them a drawing of an object familiar to them, and they can immediately recognize what it is. So it's pretty clear, I think, from these studies that for sort of these very basic line drawing styles, someone who's never seen a drawing before can understand the shape, or at least they can recognize the objects from the images. And in fact, this has also been done with infants, and even there's some very limited evidence from chimpanzee studies as well. Moreover, there's evidence that line drawings are processed by the same visual pathways as natural images. Recognition times and recognition ability is similar between photographs and drawings. And there's a few fMRI type studies that show that the cortical responses in the early vision system to photographs and to line drawings are quite similar once you get past V1 and like the very, very early visual processing. So there's been a variety of discussion of geometry of occluding contours and like how the geometry of these lines work in the perception literature, particularly the really important work by Kundring, but this work doesn't really address why we would recognize these curves as occluding contours. From what I can tell, kind of the conventional wisdom, at least from a bunch of vision and neuroscience, people that I've talked to is what I'm going to call lines as edges. And there's only one paper I've actually found that actually presents this theory by Simon Kavanagh. And the observations, the key ideas are as follows. If you take an edge detector and run it on a photograph, often the result you get looks like a line drawing. And moreover, we know that the visual cortex, that is the first stage of visual processing in early vision, includes edge-sensitive neurons. So in short, we know that edge detection does happen in the visual system. And so the hypothesis is that line drawing activates the same cortical response as an image. Or in other words, line drawings work because they look like edge detection, and we know that edge detection happens in the brain. So I've heard versions of this a lot, but I think once you actually try to formulate this as a real theory, there's all sorts of problems come up. One is that this edge detection observation works for certain lighting conditions and certain views, and for others it doesn't. There's lots of photographs where if you edge detect it, it doesn't look like a line drawing. But moreover, I think the more fundamental issue is that vision is not just edges. We are sensitive to things besides edges, and there are many images for which the edge detected version of the image, as compared to the original image, give you a very, very different percept. And it's because we are sensitive to things besides edges. So something that only focuses on edges, I think it's not a very convincing theory. Here's another example on the right of a photograph where I think you perceive a face, and on the right you just see a jumble of lines, even though the right image is an edge detected version of the one on the left. And even beyond that, I think, in this talk, I'm really focusing on very basic styles of lines, things that would be recognizable to someone who's never seen a drawing before. But ultimately, I feel like I think these ideas will, in the future, be generalizable beyond just line drawing. And I think that our perception is not just lines and photographs. There's this vast range of visual styles in which people can illustrate and draw in. And ultimately, down the road, we want a theory which is going to encapsulate all of these things. And something that is focused on edge detection, I don't think can generalize in any way, and will capture all sorts of different artistic styles. So the idea I want to explore in this presentation is that line drawing perception is a consequence of realistic image perception. That is, if you or some system has the ability to interpret realistic images, then it will also be able to understand very basic line drawing styles. And another way of formulating this is the following prediction, that if you train a vision system to do human level robust shape perception from a single natural image, you train it on natural images, and then it can work on other natural images, then that model will also correctly perceive shape in basic line drawing styles. And when I originally submitted this paper, I made this prediction, but I didn't test it. And the reviewer said, well, you might as well try it. And I didn't really think that was going to work, but I did anyways. And so I got the then state-of-the-art single image depth estimation technique called MIDAS. And it's pretty impressive how well it works, that these are two test images I fed into the network. these images here show the disparity maps that the method produces from those inputs, which is pretty impressive how well it works. This is a method which is trained on a wide variety of different kinds of natural images, but there's no artistic drawings or paintings or anything in its training set. It's a neural network with a bunch of specific features trained on natural images. And when I ran it on a bunch of drawings, it actually works pretty well. So here are a few disparity maps that come from that method, trained only on natural images and tested on a set of line drawings. And the video here may or may not be coming through well, but you can get just a little sense of how the depth map applies to these images. If the video doesn't work here, don't worry about it. Now, of course, that method doesn't work on every line drawing. It's only working, I think, on images that are in the class of scenes included in its training set. Okay, so I find those results encouraging for the hypothesis. So the next question is, why would that be? And so my goal here is going to be to explain line drawing in terms of realistic image perception. So again, why is it that a viewer who has only seen seen natural images before, why would they be able to interpret shape for line drawings as well? And for this, I want to turn to the non-photorealistic rendering literature, which has been alluded to in some of the previous talks. And in case anyone here is not familiar with it, generally, non-photorealistic rendering are a set of computer graphics algorithms whose goal is to generate artistic styles of images from 3D models or from photographs. So here's an example of a method that starts with a 3D model and produces a line drawing from it. And there's been an enormous range of work of this over the decades. I think this is the oldest problem in computer graphics, those papers from the 1960s that work on it. And people have shown you can capture a lot of different visual styles and visual effects using this class of algorithms. It's been shown up in a variety of video games and feature films as well. And I think that in a way, NPR algorithms provide us with a sort of general model for representational art. They describe spaces of transformations that can happen to models or 3D that describe some of the things that artists do. And they're not comprehensive, and they don't describe the process, typically of what artists are doing, but they describe the phenomenon of what we see in the results in many ways. One of the main building blocks of NPR, at least for 3D, are the occluding contours, which again originate in the perception in vision literatures. And so for a simple object, we can compute the occluding contours, and we get, with some tune shading, we get a nice cartoon drawing of an object, and we can stylize it. And so that's why occluding contours are so important for artistic styles. There's a conventional description of occluding contours, which I'm not going to go into here, that I imagine a lot of people here may be familiar with, but I want to present a different view which emerged in the NPR literature in sort of the 2000s and 2010s. And the idea is as follows. We're going to start with a 3D model, and we're going to render it with a diffuse headlight view. So we're getting rid of all the texture, and we paint it with a matte material, so it's just diffuse reflectance. We get rid of all the lighting from the scene. The only light source is a headlight placed at the viewer's position. And so this is the rendering you get as a result. And so it's basically the reflectance at a pixel is just n.v, the surface normal, not the view vector. And if we zoom in on this image, it turns out that the black pixels are the occluding contours, which is fairly straightforward to work out from the math, although I'm not going to go through that here. If we trace through those black pixels, just find the darkest parts in the image, then we get basically a sensible line drawing that is based on the occluding contours. But we can go beyond the occluding contours. And if you look at the shaded image on the left here, there's actually this dark valley, this sort of dark ridge here that we didn't draw before. But if we do draw it, then we get even a much better line drawing. And that's produces the result on the right. And these sets of curves now are called the occluding contours and the suggestive contours. And there's a sequence of papers that introduce these ideas in a variety of different forms. These citations I have here by Pearson and Robertson, DiCarlo et al., and Lee et al. Are kind of the main ones that introduce these ideas. And we also had work that really view this as image approximation, that if we thicken the strokes according to the thickness of these valleys in the image on the left, then we get these sort of nice varying thickness strokes as well. So as a result, for a given 3D model, we can approximate this diffuse shading with a set of lines that captures pretty well a lot of the things that some artists would typically draw for this. Obviously, this doesn't look like a human made the drawing, but a lot of the lines seem right. And this really is, it's not specific to that particular shading style. So if we apply that same kind of valley detection algorithm to this image on the left, it captures a lot of pretty sensible lines. It misses a few things where the model really is very different from the headlight rendering. But overall, the sort of valley detection procedure does a reasonable job. And in a sense, again, we're sort of approximating, finding the darkest parts of the image on the left and approximating them with thin lines. So this dark, I hope you're seeing my cursor, but this sort of this dark band by her left, viewer's left cheek becomes a dark line. So can we validate these algorithms? There's been a few attempts to do so. One thing that we did for our line thickness method was my student took this image here, built a 3D model by hand in Blender to look like that shape, and then rendered it with our algorithm. And it matches, I think, the style pretty well. And there's two parameters here. There's no machine learning or anything. It's just a completely procedural algorithm. But the more convincing evidence, I think, comes from Forrester Cole's thesis, where they asked artists to make accurate drawings of a set of 3D models, and they found that the existing algorithms, similar to the ones I described, are quite predictive of where artists draw lines, with something like 70% agreement or 80% agreement, which means that these methods are on the right track. And in all this talk and in some of the previous talks, people have discussed more recent and more general data sets like Yulia's that build on these ideas. But I looked at this one as kind of like the first sign that this is really on the right track. I also just want to mention as an aside before I return to perception, we've been doing some recent work on trying to combine some of these NPR ideas with modern machine learning. So at CDPR last year, we presented neural contours where we have a deep network that learns which pixels to activate for these kinds of line drawing styles. And this week at ICCV, we've presented a method for learning to stylize geometric line drawings. So on the upper left here, the artist is given geometric lines from an image, and they just draw in pencil or pen or whatever a stylized version of those lines. And then from that single example, our network learns to predict and generalize that style to other kinds of line drawings. And so these two methods are sort of two pieces of trying to really build out the differentiable rendering pipeline so we can do end-to-end training of NPR algorithms that use both geometric insights as well as all the benefits of modern deep learning and end-to-end training and so on. Okay, so now back to the perception question. So why is it, given this background from computer graphics research, why is it that line drawings work? And again, I want to reiterate this assumption that if you see a new scene you've never seen before, even though you don't know what the materials are or the objects, if it is something that could have happened in the real world, then you can understand the shape in the scene pretty well. And this is even robust to things like degradation of the image and fog and other things that would interfere with vision. You can still interpret some elements of shape in those cases. And my main hypothesis here is that the human visual system interprets a line drawing as if it were some corresponding realistic image. So the visual processing pathways respond in the same way to a line drawing as they would some hypothetical corresponding image. And that corresponds to this sort of headlight arrangement that I described earlier. So when you see this line drawing on the lower right, that more or less could have been produced by a particular set of geometry and white matte materials and a point light source and a given arrangement that could have happened in the real world. Or in other words, another way of saying this is that for the drawing on the left, there exists a photorealistic interpretation the image, the vision system could see the image on the right and treat it as if it were the image on the left. And based on this hypothesis, I would make two predictions. The first is that what I said before, that natural image understanding algorithms that work for the broad class of real scenes should be able to understand line drawings, and I had those promising results from Midas before. But I would also predict that the cortical responses to line drawings are very similar to responses in these headlight images. So if you show a viewer the image on the right, or feed it into a neural network that accurately models early human vision, the cortical responses, the neural activations will be very similar between the image on the right versus the image on the left. And there's a variety of papers within neuroscience and cognitive science that have done fairly similar tests. And so all the methodology exists, I think, to do this test. Moreover, I think this idea, another way of thinking about this corresponds to this idea of as art as inverse vision. And this is an idea that goes back at least to the classic art historian Gombrich. Gombrich sort of compared an artist to being like a lockpicker who has keys and tools fumbling around a lock, trying to unlock the keys to perception, trying to they don't understand how the lock works, but they know that with enough experimentation, they can come up with something that's going to achieve goals. So if you imagine an artist who's never drawn a picture before and a viewer who's never seen a drawing before, but they can understand the real world, and the artist wants to convey a particular shape and they only have a black pen, what can they do? Well, they can draw a line drawing, and when this theory I presented essentially argues that this kind of line drawing answers this question. It is the solution to the problem of how do you portray shape to a viewer given only black and white lines and no hatching. And we can more broadly think of art as perceptual optimization. And there's a number of papers from long ago and more recently where people are beginning to formulate stroke placement algorithms as optimization with respect to perceptual loss functions. And I think this is a pretty exciting direction to go. I just wanted to reiterate a few assumptions that I've been making throughout the talk, just to be very concrete about these things. One is I'm only talking about a viewer who's never seen a drawing before. So this is only for all of us in real human society, we have a lot of experience and cultural conventions about drawings that we can see, like the industrial drawings that I think Ola showed in the previous keynote, like these cross-section lines. I think those, for example, are the results of cultural conventions. They may or may not be understandable to someone who's never seen a line drawing before. So generalizing this theory to those classes of drawings, this theory is not capturing those. I'm just focusing on a very basic line drawing style. And finally, so far, I've only talked about smooth surface contours. But to this last point, I think that there are other kinds of curves that we can capture within this sort of lighting or shading understanding of how lines work. One very simple case are inverse lines, and this is something a reviewer of my paper asked about. When you see white on black, like on a chalkboard outside of a cafe, this obviously doesn't fit the kind of shadow lines I was describing before, but I think they're really well explained by rim lighting, which is when you have light sources off to the side or slightly ahead of or behind the subject. These three images here are all photographs, and I think that these lines, these curves, these like highlight regions look a lot like line drawings. And so to me, if I take the same drawing and invert it, the image on the right, it's possible I've been looking at this too much, but the image on the right looks to me like a ceramic cup in daytime with rim light, side frontal lighting. Image on the left to me looks like sort of an obsidian black cup at nighttime with sort of more rim lighting. Hatching is another one that I feel like doesn't require a whole lot of explanation because it's often very much about reproducing tones that match what we would see in natural images. Increases are, I think, the most challenging thing for my theory. I don't want to go into, so a crease, but what I mean is like the sides of a box. These are like C1 discontinuities in the shape of the object. And so in the papers, I kind of worked through a set of hypotheses as to why creases might be understandable in terms of the lighting theory, and I'm not really sure which of those different theories is the best one. And moving beyond just simple line drawing, again, I think it's worth thinking about how do we perceive shape and identity in so many different styles? Like we seem to be able to disentangle the visual style of an illustration and drawing from its underlying shape and object content. And this seems like another optimization. This seems like, or there's some inference process which is explaining some elements of the scene to style and parsing them into their underlying shape and object information. I do find it encouraging in that Midas paper, when they did publish the final version, they did do tests on the line drawing that I use, as well as some other different artistic styles, and they were also getting quite good depth maps from these paintings as well that have a few different styles. But it still, remains open. How do we, think about parsing an image as, separating the style from the drawing from the underlying style? And this speaks to a lot of the kind of stroke, sketchy stuff that you might do in sketch-based modeling. One artist may draw in a very precise style, another one might do a lot of sketchy things, and you really would ideally, interpret which kind of line is which in terms of the artist's overall style. So to summarize, my main claims are that we can understand line drawing in terms of realistic image perception, in terms of this particular shading model of that can generate line drawings. And more broadly, this can be thought of as providing an optimization formulation for drawing interpretation. That is, creating drawings is, perceiving drawings, in a lot of perceptual theories can be thought of as an optimization process for inference. Creating a drawing is something which optimizes for a viewer's perception. And so we can think about generalizing these basic styles through this sort of optimization understanding of everything. All the specifics in this hypothesis I'm presenting are open. There's lots of questions that I don't have answers to about, like, what are the particular lighting assumptions. There's a lot of tests and predictions to be tested that I don't have the resources or expertise to do human vision experiments and cortical modeling studies, but I hope someone is interested will be able to do them. And again, I think we can think about generalizing these ideas beyond line drawing, develop algorithms for this theory, and use them to interpret and understand sketches and drawings and other types of illustration. Thank you.
Thanks, Aaron, for this very thoughtful presentation. I think it opens up a lot of questions and hopefully a lot of follow-up work. Please use the chat for questions. I see several hands up, so we'll start with Adrien.
Well, thanks a lot. It's nice to see the theory that unifies NPR and perception and shape reconstruction. You mentioned several times that at least for now, the theory doesn't extend to other types of lines like cross sections and cross hatching. And yet I'm wondering if it could, because at least those lines are often aligned with principal directions of curvature. And my intuition would be that it could be related to texture perception or highlight perceptions, which are often distorted by curvature. And so because we are used to perceive such shape distortions in dense patterns in real photographs, that might explain why we perceive so well curvature from those lines. Did you think along those lines, or do you think it's out of the theory completely?
Yeah, I think actually I spoke a little bit too fast when maybe talking about cross-section lines. So I completely agree. So there was a paper by Landy, Imamasian, and Perception in 1997, where they showed that viewers do perceive hatch lines as principal curvatures, with the idea that they may correspond with some texture generic perception theories around it. And in fact, in our SIGGRAPH 2000 paper, we did use principal curvature directions for hatching. So I think with the cross-section lines, there's a little bit. So I think the story is fairly strong for hatching as principal curvatures, because these do seem to correspond a lot to texture perception that and there is a basis for viewing the hatching lines as being corresponding principal curvature directions. I think, with I don't know if it's worth getting into the details of the sort of like cross-section lines, which are a little bit singular, a little different from this sort of texture, but I think they're pretty similar. So I think probably the answer is yes, that they could be explained that way.
Thanks. There's another question, EJ.
Okay, yeah, thanks, Aaron. So very sort of like insightful talk, and I have two questions. I'm trying to decide which one I should go for. Okay, so I think I should go for the second one. So I think I like this link between line drawings or sketches to the real, like, natural image statistics, right? So something we're working on now, and something I've been really keen to work on for the past few years, we're just starting now, is actually to think how the saliency transfer. I think maybe Sven did something like this in scene sketches as well. So if your theory holds, I mean, if I understand the theory correct, right? I mean, correctly, then the saliency that we can somehow extract from your drawings might be a good way for us to understand how saliency works in the natural world. So for example, I mean, this is like a quick example. So if I draw something like, a cat's ears first, whiskers first, that basically means those parts are important, right? And those saliency information is easier, or we have more cues to rely on to extract from drawings, because you have the speed, you have the sort of like the drawing order information, all of that in drawings, right? And then also the human draw, they inject their understanding into the scene. So I'm thinking that maybe there's a relationship there. So what's your views on that? Or did I make myself clear?
Yeah, I mean, there's definitely relationships between all those things. I don't know if these things, hold the key to understanding. I think so. My general understanding of saliency, and by saliency has a few different meanings. But if we talk about like where do eye gaze fixations occur, they're going to be in high information points, and so we can look at a line drawing and saying which parts of that hold the most information for a viewer, and has the artist been successful in attracting the eye to the right places. And there are various kind of artistic techniques one might use to control where the eye goes by adding detail or removing detail. I view those as techniques for guiding the visual system to the right interpretation. And I think line drawings provide a useful test case for thinking about saliency. Beyond that, I'm not sure. I have more to add. Speak to your question, and maybe I misunderstood it.
Yeah. So I mean, I don't quite understand it, but then what I really, really want is really relate drawings, sketches to natural images, right? I think, and then like I said, there's more cues in the drawings themselves that maybe can help us. So that's like I don't know, just a live discussion really. So yeah, but thank you very much. Yeah.
I think that's a really interesting thought, how line drawing can help understand natural images better. Yulia has a question next. Yulia, do you want to call out the question instead of
Sure, I can ask the question. It's about in the previous study by Cole and colleagues, they provided people with a reference image which had a fixed shading. So I'm curious, if you provide the same shape which is rendered with different kind of lighting, do you have some estimate how consistent the people will draw in where they draw the lines? And I also wondering, like, if you provide some really bad lighting, let's say, like it very poorly will highlight certain features of the 3D shape, will humans still try to emphasize these features, or they will try to reproduce what they see in the image?
I think partly it depends on what your goals in the drawing are. So what are the instructions that you gave to the artist when they're doing this task? If you tell them your goal is to make a line drawing that only depicts shape and don't do anything with shading or convey anything about the lighting, then that's a very different task than if you tell them make a nice picture of this photograph, and when they might try to include a lot of the lighting information hatching and shading and thickness of strokes. And certainly, like if you have very bad lighting, the artist may not even be able to tell what the shape is, in which case that'll also affect the lines they draw. But I certainly believe that if you vary the lighting and give the artist enough information about what you're looking for in the task, and they're cooperative, and you're very clear about what you're looking for, then I feel like my guess is the lighting would not have a big impact on the lines that they would draw.
Okay.
But that's
curious to see. Yeah, but I'm also curious about how people can draw differently depending on the task where they would put the lines task driven. I will pass to other people.
So let me see who's next. Kaiyue.
Hi, thanks Adrien for the talk. So I have two quite quick questions. So first question is about the line drawing. So the utility or efficacy in solving the real world perception problems. For example, we know that neural networks are quite sensitive or biased towards local textures and sorts, right? So it's not that very robust and generalizable sorts. So, and then what's your thought on whether line drawing can help better to solve real world perceptual problems but in autonomous driving? And or do you think is there some unique, in your talk, definitely you said like, line drawing do convey kind of like the same information as what's normally in the human eyes perceived by appears to the natural images. And do you think in the neural network slides, there's some unique information in the natural image statistics, or line drawings just should be suffice? So basically, computers should be taught to do real world perception on line drawing data so as to perceive better. My second question is, so in my opinion, that so sketching and line drawing, and especially line drawing you present here, I think sketch is kind of a freehand drawing by a human. It's kind of a compressed information bottleneck of the line drawings. So do you have any thoughts in mind how to quantify this kind of like this abstraction and this information gap, or even the saliency gap between the what human can really draw and what's kind of like the line and underline drawing? So is there any way to quantify their differences? Thank you.
I don't think I fully understood that, so the audio broke up a little bit there. I mean, I can respond to one or two things. One is that I think definitely drawings and all visual art and all visual representation do not reflect human perception. When we perceive in the real world, there's a huge amount of information we're gathering that's interpreted by the visual system in particular ways. And any drawing or any photograph is just taking a tiny slice of that tiny fraction and portraying that on a flat, low resolution, low dynamic range image, compressing it in different ways. So artwork is really just this technique we've developed to activate the visual system in various different ways. So I really think that line drawing perception is, or like art perception in general, is related to but very different from real world perception. With respect to quantifying the semantic gap, I think I've seen some work on people trying, comparing how do people describe, textually photographs versus line drawings versus, other experiences. That could be one way, comparing the responses people have to these different stimuli could be one way to measure what information is present in a line drawing.
So, I'm sorry, I'm sorry to switch on a little bit. So, so basically, do you have any kind of thoughts like, so to me, like definitely if you talk about stroke numbers and also, so sketch definitely have much less stroke numbers, let's say, compared with the line drawings you present in your talk. What I want to say is, do you have kind of like from information bottleneck point of view that can really, have some insightful thoughts on their differences? Because I can't really quantify myself sometimes, but I always think it must come to me that, so there is some differences, but it's really hard to quantify in my view. So like,
try to understand the purpose of quantifying these differences.
Yeah. so we don't draw. So basically, I mean, I think line drawing contains much more visual elements than the normally what people can usually draw. Do you agree with that, or you don't?
I mean, people often do only draw a few lines, and a lot of that is function of convention or the fact you can just indicate a few strokes.
Maybe it relates to how much time people have to draw this stroke, and that's the amount of detail they would add. In interest of time, I see that we're slightly running over time.
Oh yeah, thank you, Adrien. Sorry, yeah, thank you.
One last question, Sven, please go ahead.
Thanks, Niloy. Great talk, Aaron. Really appreciate the message. Question: clearly, your work on line drawings has, pushed the envelope of shape perception because you're focusing on line drawings. And as we know, in the more traditional RGB community that looks at image understanding, with the exception of some recent work that's tried to disentangle shape from appearance, they have not focused as much on shape. And I guess I'm wondering more generally, how can your research better inform a more traditional pipeline that tries to understand RGB images? How can we use your findings to help guide these networks to exploit this kind of shape information more readily?
Honestly, I'm not really sure it's that useful for natural images, because that work is so effective. I think that, if anything, I think okay, so this is very much a flight of fancy here, but I think one thing that this kind of work shows is that human visual perception of photographs and images is much more than just photographs. And we have some ability to somewhat disentangle visual style, artistic style. And in general, if we want to model visual understanding and visual perception and build algorithms that understand our images the way we do, then we need to model and understand broader notions of style than just photography. And that it's something that we as humans seem to do fairly effortlessly. And so solely focusing on photographic understanding is a narrow slice, an important subset of human perception. So I guess maybe my answer is not so much that I don't know that this actually informs perception of natural images, but it maybe says a little bit the problem that we should be focusing on is a little bit broader.
Great, thank you.
Maybe one thought there, it would be really interesting. I don't know, Aaron, if you've tried it, to see like the VGG activation patterns on paired images, where one is a natural image, another is like an artistic sketch of that, and see if there's some correlation, and where the natural image activation pattern disagrees with the line drawing activation pattern. But I think that's a question for a later time.